Institute of Aeronautical Engineering Autonomous Dundigal. My name is N. Venkat Sai, roll number 2395180226. Subject Electrical Energy Conservation and Auditing. Subject code AWD22. Topic Analyze the importance of capacitors in reducing distribution losses. Department Electrical and Electronics Engineering. Capacitors reducing distribution losses. Harnessing reactive power to enhance grid efficiency and minimize energy waste. The challenge power distribution losses. Power distribution system losses significant energy during transmission and distribution. This losses occurs in two primary forms: resistive losses, I2R losses in conductors, and reactive power losses in the network. In many regions, distribution losses range from 5 to 15% of total generated powers, a sustainable waste of resources and revenue. When reactive power circulates through the system without performing useful works, it increases current flow through transmission lines and transformers. This elevated current generates excessive heat, accelerating equipment degradation and driving up operational cost. Addressing these losses is critical for utility companies seeking to improve efficiency and reduce environmental impact. Resistive losses: heat dissipation in conductors due to current flow through resistance. Reactive power losses: wasted energy from reactive current circulating through the network. Economic impact: direct revenue losses increases operational expense from utilities. Understanding reactive power and power factor. Power factor is a critical metric that measures how efficiently electrical power is being used. Real power measured in kilowatts perform useful work in motors, lights and equipment. Reactive power measured in kilowatts suppose magnetic field in inductive device but produce no direct works. When reactive power dominates, the power factor decreases, forcing the system to draw more current to deliver the same real power. A power factor is 0.0 is ideal. All power performs useful work. In most distribution systems, power factors typically range from 0.85 to 0.95, meaning 5 to 15% of current serve no productive purpose. This reactive current increases line losses exponentially due to the I-square relationship. By improving power factor close to unity, utilize dramatically reduce distribution losses. Real power, actual work performed, measured in kilowatts, power motors, lights, heaters, and productive equipment. Reactive power, support magnetic field in inductors, measured by kVr, circulates without performing useful works. How capacitors improve power factors? Capacitors generate leading reactive power which directly oppose the lagging reactive power produced by inductive loads. When strategically placed in distribution networks, capacitors neutralize excess reactive power, bringing the system's power factors closer to unity. These fundamental principles reduce the total current flowing through lines and equipment, directly decreasing I-square losses throughout the networks. The process is dynamic and precious. Capacitor banks automatically switch on and off based on load conditions, maintaining optimal power factor even as demand fluctuates. Modern systems use switching capacitors banking with sophisticated controls to respond the real-time measurements. By reducing reactive current requirements, capacitors allow the same amount of real power to be delivered with lower line losses, reducing voltage drop and improved system stability. Inductive load create logging reactive power. Capacitor bank generates leading reactive power. Net effect reduced total reactive power, improve power factor closer to unity 1.0. Types of capacitors used in distribution system. Distribution network employed several capacitors technologies, each suited to specific applications and operational conditions. Understanding this optional is essential for designing effective losses reduction strategies. Pole mount capacitor. Compact units installed directly on distribution poles, cost effective for localized reactive power correction or medium voltage levels. Substation capacitor bunks. Large scale installation of substations provide bulk reactive power support, enable centralized control and maximum efficiency across wider service areas. Switched capacitor bunks. Automated unit with thyristor or mechanical switches enabling rapid response to load variations. Maintain optional power factor across changing demand profile. Distribution level capacitors. Medium voltage installations addressing reactive power at secondary distribution points. Bridging between substance and end use areas. Strategic placement of capacitor for maximum impact. Optical capacitor placements is both science and strategy. Engineers analyze load distribution, voltage profiles, and reactive power requirements to identify the highest impact locations. Generally, capacitors should be placed where the addresses reactive power consumption closest to the source, minimizing transmissions distance and maximum losses reduction efficiently. A hierarchical approach proves most effective. Bulk capacitors at substance handling system wide reactive power needs, while distributed units address localized demand. Load flow studies and power flow analysis guide placement decisions. Coordinating capacitors location with other grid equipment, transformers, regulators, and protective devices. Ensure harmonious operations. Regular monitoring and analysis allows utilize to optimize placements over time as load patterns evolve and new equipment is added. Load analysis. Map reactive power demand across the distribution. Voltage profiling. Identify weak points and voltage drop hotspots. Candidate location evaluation. Access technical and economic availability at potential shoots. Optimization simulation. Model loss reduction impact at different placements. Implementation and monitoring. Deploy and continuous measure performance. Benefits beyond loss reduction, voltage stability and capacity. While reactive power correction and loss reduction and primary benefits, capacitors deliver significant secondary advantages that enhance overall grid performance. By, by maintaining reactive power balance, capacitor stability voltage profiles throughout the distribution system. This voltage stability prevents equipment damage, extends transformer life, and improve power quality for end consumers. Capacitors also effectively increase systems capacity without requiring cost infrastructure expensive. By reducing reactive power circulations, available transmissions capacity increase. Utilize can serve more consumers accommodate higher peak demands without upgrading lines and equipment. This deferral of capital expenditure represents sustainable economic values. Additionally, improved voltage and reduced losses enhance equipment reliability, reducing emergency in repair and service interrupts that cost utilize and customers alike. Loss reductions decrease I-square losses, low reactive current, voltage stability, maintenance steady voltage within acceptable range, reliability, reduce equipment stress and service interruptions, capacity increase, and enables higher loads and exciting infrastructure. Case study, real world impact and capacitor banks. Numerous utilities worldwide have achieved measurable success deployed capacitor solution. These real world implementations demonstrate the tangible economic and technical benefits of strategic reactive power management. Major urban utility 2019 to 2021. A metropolitan distribution system installed 47 switches capacitor bunks across 12 substations. Within 2 years, System losses decreased from 8.3% to 5.8%. 3.5 percentage point reduction translating to 12.4 million annual savings. Power factor improved from 0.89 to 0.96 and advantage stability metric improved 18%. Rural complicative 2022-2022. Rural complicative deployed 23 pole mounted capacitors across 340 kilometers of distribution line. Distribution losses fell from 11.2% to 8.4%. The cooperative deferred 8.7 million in planned substation upgrade by 5 years through increased system capacity. Regional Transmission Company 2018 to 2023. Multi-state deployed of 156 capacitors unit achieved 6.2% system loss reduction, preventing approximately 847,000 milliwatts per hour annual waste. Carbon emissions advised to exceed 42 425,000 metric tons annually, equipment to removing 92,000 vehicles from roads. Program units loss reduction annual saving times. Urban utility 47 units 3.5 load reduction on 12.4 million annual savings 2 years. Rural crop 23 units 2.8 percentage loss reductions 4.2 million annual savings 2 years timeline. Regional transmission 156 units 6.2 percentage loss reduction 28.7 million annual savings 5 years. Economic analysis. ROI of capacitor installation. Capacitors installation represent the capital investment for seeing measuring returns. Capital cost range from 15,000 to 45,000 per unit depending on type of capacitors. Typically 2.5 installations. Operating and maintenance cost are minimal, approximately 400 to 800 annual per unit for monitoring and oceans compound replacement. 25K average installation cost per 3 MVR unit installed. 3.8 payback period years, typical range 2 to 6. 350% average lifetime ROI over 20 to 25 lifetime. 87% cost saving versus alternatives compared to network upgrades. Conclusion. Optimizing grid efficiency with capacitors. Capacitor based reactive power correction response one of the most cost efficient strategies for reducing distribution losses and enhancing grid performance. By improving power factor and stability voltage, strategic capacitor deploying the delivers immediate and sustainable benefits. Lower energy losses reduce operational cost, extend equipment life, and enhance system reliability. The technical advantages are clear. Modern switch capacitor bank with sophisticated control provide dynamic, responsive, reactive power support tailoring to real-time grid connected. The economic case is equal, completing relativity. Modern capital investments generate returns to exceeding 300% over equipment lifespan within payback periods typically under 4 years. As utilities navigate the challenges for again infrastructure, increasing demand and sustainability pressure, capacitor optimizing emerges as a strategic priority, whether deployed at sustainable level for bulk support or distributed across networks for localized corrections. Capacitors empower utilized to more with exciting infrastructure, reducing waste, improving reliability, and supporting the clear energy transition. Technical excellence. Proven losses reducing and stability improvements. Economic values. Strong ROI with 3 to 4 years back typical. Operational benefits. Enhanced reliability and extended equipment life. Sustainability impact. Significant carbon emissions reduce. Thank you.